back everyone to another Clued video. Today for Organic Chemistry 1 we are going to be talking about alkene reactions you should know for this semester, as well as some simple tricks on how to remember them.
So I'm just going to write out the major alkene reactions that you should be knowing for organic chemistry in college. I'm going to use some abbreviations on this chart that I made. FGT stands for functional group transformation. Ox is oxidation. Red stands for reduction. And CC is the carbon-carbon bond formation. And this just helps organize the types of reactions that we'll be doing, and I'll write that on the far right column. So for our first reaction, the starting material is going to look like this. This holds true for tertiary, secondary, or primary structures. It's going to be an elimination 2 reaction, and you're going to add some type of base, and since you're getting the most substituted product, that is the Zaitsev product, and the base here can be NaH, DBU, or DBN. These are smaller, smarter bases. The second one, we're going to do the same thing, except we're going to add a bulky base, in this case, tert butoxide. This is a very common bulky base in organic chemistry reactions, and as a result, since it's really bulky, it's going to leave the least substituted product, or the Hoffman product. And I'm just going to show a quick trick that I use to remember which one is most substituted or least substituted. This is Hoffman. You could also think of it as the Kaufman. Coughs in people's faces, he's really nasty, and no one wants to be by him. Therefore, the Hoffman product is the least substituted product, farthest away from everything that's going on. On the other side of things, this is Zaitsev. Everyone likes her. Her hair smells super good. She's popular. She's super smart, and everyone likes her. She is where all the commotion happens. She's generally in the middle of things. Therefore, Zaitsev forms the most substituted product. No one wants to be by Hoffman. Poor guy. For our next reaction, we're just going to add water or something attached to OH. In this case, you're going to get the Zaitsev product. In this one, the halogen is going to attach to the most substituted position, therefore forming the Markovnikov product. Here, rearrangement is possible, meaning that if there's double bonds, it can move over to form the most stable configuration. When you add peroxide to this reaction, you end up getting the Anti-Markovnikov product, which just means that instead of the substituent or the larger substituent going towards the most substituted position, it goes to the least substituted position. A quick trick to remember this is thinking about it as a popular guy versus someone who is more introverted and likes to stay away from the crowds. This is Mark. People are always by him. He's always with the crowds, super popular at parties, and he's always where the commotion is. This, on the other hand, is anti-Mark. He is like Mark, however, he is the opposite of Mark. He tries to stay away from the commotion. He'd prefer to have a quiet night in reading, which is also super cool. Therefore, Markovnikov products, the substituent is at the most substituted position on the product, whereas the Anti-Markovnikov product is a little bit more introverted and the opposite at the lesser substituted product. When you add water in acidic conditions, you can have two of these products, and rearrangement is possible. However, it's still considered a Markovnikov product because the substituent is going to the more substituted position than the hydrogen is. Similar situation holds true for this next reaction. However, rearrangement is not possible in this. So although a little bit more complicated in application, you can ensure that you will only get this type of product. Okay, here is an anti-Markovnikov reaction because the OH is going to the lesser substituted position. H and OH are added in this case, and they are syn. Syn just means that they are facing the same direction. Again, the X represents a halogen like chloride. Here, with X2, you end up having an anti-addition. This just means that they are both being added to break that double bond. However, they are facing opposite directions. When you do the same reaction with water, an OH is added instead of that X. The OH goes to the most substituted position, and also there is an enantiomer present. Again, the R just means an extra group. When you add the RCO3H, that temporarily forms the epoxide. And then when you add the water, it breaks apart the epoxide because those aren't very stable compounds, and it adds the two OHs in an anti-diol position. The diol just represents the hydroxy groups, and anti because they are facing opposite directions. And then again, the enantiomer is present as well. These next two reactions do the exact same thing. There's just differences in the types of reagents used and their cost. In this case, it's forming a syn diol plus the enantiomer. And you use this one when you want the OHs to be added in the same direction. This next one, I kind of have a funky way of remembering it. When you add something like MCPBA or MMPA, you end up forming an epoxide, which is just the little triangle with the oxygen on it coming off of the two carbon atoms. MCPBA reminds me of a rapper name for some reason. A friend of mine, when I was taking the class, was always calling epoxide Little Doritos. So MCPBA sounds like a rapper name. Add that W. The rappers are what wraps up Doritos, and that is how I remember that MCPBA forms the epoxides. So for this next alkene reaction, you're able to add an ether group. This is a Markovnikov product because the substituent is adding to the most substituted position that it can. And these stars I'm drawing just mean that you might not have gotten to this part yet in the semester. When you do this reaction, I just put these numbers here just for reference. You're going to get two products. So the two halogens can be added to either the 1 and 4 positions or the 1 and 2 positions. And when it's added to the 1 and 4 positions, that double bond rearranges to go to the middle to form a more stable product. It's important to note that in this case, X represents bromine or chlorine. So when you have a bromine or a chlorine attached to a hydrogen and you put it at 0 degrees Celsius, you end up getting the 1,2 adduct. This just means that it's adding at the 1 and 2 carbons. It's breaking that double bond. And that's the only part of the atom that's being changed in the product. When you do the same exact thing, but at 40 degrees Celsius, which is a lot warmer, you get the 1,4 adduct. Alright, just 2 left today. This next one is my favorite reaction of all time in orgo because it is super, super easy to remember. When you have H2 and you add something like palladium, platinum, or nickel, you just break that carbon bond, and the two hydrogens just get added on. And the palladium, the platinum, and the nickel, you just can choose one of them for the reaction. It acts as a catalyst, and it helps the hydrogens break that carbon-carbon double bond. It is a syn addition, so you could draw the hydrogens as like dashed lines, and then one of those carbon substituents on the left-hand side into a solid one, or vice versa. This is a reduction reaction, and an easy way to remember this one, at least for the palladium part, you could say PD stands for please destroy, and what it's destroying is the carbon-carbon double bond. And it's reducing it and adding those two hydrogen atoms there. Alright, for the last reaction, not actually sure if this counts as an alkene reaction, but I thought I'd include it in this video. It can't hurt. It's an ozonolysis problem. By adding O3 with DMS, you're essentially just splitting the double bond in half, and you're, strangely enough, adding oxygens to either side. So, for this one, just make sure you write those two products that are left. Okay, great work everyone. That's going to conclude the video for today. I hope you have a great rest of your day, and good luck in the upcoming semester. Thank you.